Welcome to ECE 376, lecture number 16, take 2. Student t-test with two populations. Now, the student t-test is probably the most common, most important test you're ever going to see in statistics. It is the test of a mean. From the central limit theorem, most data, under very general general assumptions, almost all data will approach a uniform distribution. With that, we can do a t-test. With a t-test, I can take a single population and test. What's the probability it's greater than a mean, like a set of transistors have a gain of at least 300? I can find the confidence interval. So when I collect the data, 90% of the time it'll wind up in a certain area. I can tell you the 90% confidence interval for the mean. Stuff you can do with a single population. Today we're going to look at what happens if you have two populations, such as I've got two people competing, playing Hungry Hungry Hippo, or jumping, or something like that. I want to compare the two to find out who's got the higher mean. Well, what you have is something like this. I've got two populations, A and B. From the central limit theorem, their distributions will be a normal distribution. That's a basic assumption behind the t-distribution. I want to find out either if I just take one sample from A, one sample from B, what's the probability that A will be greater than B? Kind of like you're playing a football game between two teams, who's going to win the next game? Or population. Which population has the higher mean? Who's the better team? So that's what we're looking at. So suppose I just want to play a single game. A's playing a game of football, there's a spread in its score. B's playing a game of football, there's a spread in its score. What's the probability that A is going to win the next game? Or, conversely, I've got a bunch of transistors from population A, a bunch of transistors from population B. If I just pick out one transistor at random from A, one at random from B, what's the probability that A is going to have a higher gain than B? Well, as an example, give you something concrete to deal with, let's play a game of Hungry Hungry Hippo. And Hungry Hungry Hippo, you've got two people thrashing their button as fast as they can. Whoever hits the button the most number of times in 5 seconds wins the game. So I play n games. A played a bunch of times, B played a bunch of times. From that data, what's the probability that A is going to win the next game? Well, the procedure, since I don't know the mean and standard deviation of A and B, I'm going to estimate them from the data. That gives you a t-distribution. So population A has a mean of 88, B has a mean of 76, A has a standard deviation of 8, B has a standard deviation of 6, and what that tells you is you've got these two populations. There's A and B. A has a mean of 88, B has a mean of 76. Again, it's not guaranteed that A is going to win. I could get a low-scoring A next game and a high-scoring B next game, so B could win. What's the probability that A is going to win? Well, this is kind of like the story of the fire extinguisher and trash can. I've got a solution. My solution is if I have a single normal distribution, I can find out what's the probability that you're greater than some threshold. To do that, I form the t-score. What's the distance from the mean to your threshold in terms of standard deviations? That's your t-score. I can then use the t-test to find out what this area is. Well, force the problem to fit that solution. What I'm going to do is create a new variable called W. W is the difference of A minus B. If W is greater than 0, that means A is bigger than B. If W is less than 0, A is less than B. When you add normal distributions, a normal plus a normal is a normal. When you subtract normal distributions, the means subtract. So the mean of W is just the mean of A minus mean of B. So take the difference in the two, I get 11.33. The variance adds, it doesn't subtract. And that kind of makes sense because if it's subtracted and B had a bigger variance than A, I would have a negative variance. That doesn't make any sense. And the variance also adds because I could get a low B and a high A, giving a bigger spread. A bigger spread means a bigger variance. So in this case, the variances add. It doesn't matter whether you're adding or subtracting. Since this is a square, the variances will always add. So the variance of W is just the variance of A plus variance of B, or at 188. Take the square root. The standard deviation of W is 10.89. So here's your W distribution. The mean is 11. Here's 0. That distance, one standard deviation, is 10.89. I can now find out how far is 0 from the mean in terms of standard deviations. I can find the t-score. So doing that, the t-score is the mean of W divided by the standard deviation of W, which is 1.04. So again, this distance right here, distance from the mean to my threshold, is 1.04 standard deviations. To use a t-test, I need to know the degrees of freedom. And that's actually kind of complicated. This is the actual formula for degrees of freedom. It's a function of sample size from population 1, population 2, the variance of population 1, population 2. Grind it all out, I get 7.37, which doesn't make any sense. It's got to be an integer, so round it. Roughly 7 degrees of freedom. That's the accurate way to do it. A simpler way is to just take the smaller of the two. A has 4 degrees of freedom, B has 5 degrees of freedom, so roughly it's 4 degrees of freedom. And in the limit, these two match up. If A has a sample size of infinity, then this is just really testing against a known mean. Because if A has a population of infinity, let's see, this goes to 0, and you just get the degrees of freedom of B. If B goes to infinity, you just get the degrees of freedom of A. So it's going to be the smaller of the two. Again, if A is infinity, it has an infinite degrees of freedom. B is what determines it. Take the smaller of the two. It doesn't make a huge difference on the answer, and it's a whole lot simpler. So if you have, if you have the time, grind it out, or roughly, it's the smaller of the two, 4 degrees of freedom. Once I know the t-score and the degrees of freedom, I can go into StatTrack, plug it in, and find out what's the probability. And the answer is 83.6%, so this area is 83.66%. The area to the left, all probabilities add to 1, is 16.34%. So there's a 16% chance that B is going to win the next game, 83% chance that A will win the next game. That's comparison of two means. And here's kind of what it looks like. This is the distribution for A. Here's the PDF for B. The distance between the means is your t-score. So that distance in terms of that standard deviation is your t-score. Throw that in StatTrack, I can convert to the probability. So this is the probability of the next game, A winning the next game. And notice sample size doesn't really affect the answer. A's got a pretty big spread, B's got a pretty big spread. There is a chance, a decent chance, that B's going to have a high score, A will have a low score, and B will win. The more games they play, that doesn't change the odds. B still has a chance of winning any given game. Now, a slightly different question is, if you played an infinite number of games in a match, who's going to win? Or, in other words, which population has the higher mean? Again, if I have an infinite number of games, whoever's got the highest game or highest mean will win. What's the probability that A's mean is actually bigger than B's mean? And here's my data, but my data is fairly limited. There's a chance that A's got a distribution, well, actually, it's actually a chance that this is the actual distribution. And just by dumb luck, I got a bunch of samples over here for A. Just by dumb luck, I got a bunch of samples for B over here. So it looks like A has a higher mean than B, but actually B has the higher mean. So I can't just sit there and say A has the higher mean guaranteed because the sample did. It depends upon the sample size. And the more samples I have, the more certain I am that A has a higher mean than B. So I need a measure that takes sample size into account. Where that comes from is if I estimate the mean of a population, the mean is a normal distribution. As the mean of the true mean, the standard deviation is actually the variance is the population's variance divided by sample size, or the standard deviation drops as the square root of sample size. So as I sample more and more and more, the standard deviation gets smaller and smaller, and eventually, when I have an infinite sample size, I know precisely what the mean of A is, precisely what the mean of B is. So as the sample size goes to infinity, I can see a very, very small difference. So when I form my variables, I'll do exactly the same thing I did before. I've got two populations, A and B. I'm going to form W. That's the new population. That's the difference between A and B. The mean of W is just the mean of A minus mean of B. However, since I'm dealing with populations now, the variance of W will be the variance of A plus the variance of B, and the variance of A takes the sample size into account. Again, I'm estimating the population's mean. The population's mean has the variance that drops as n. The variance drops as n. So add those two up. That's now the variance of W. This is for the population. So what I'll do is, again, you've got W as the difference between the two means. S is the sum of the variances, but now this is the variance of the mean, not the population. My t-score then is same as before. What is the mean over standard deviation? Again, for the population's mean, this is the mean of A minus the mean of B. I want to find out what's the area to the right of 0. Because over here, this means that the mean of A is bigger than the mean of B. A will win an infinite series. Less than 0 means that A is less than B. B will win an infinite series. So again, I take the same score I had before, mu sub W. Now I divide by this number, and I get 2.4. So that distance, my t-score is 2.4. I now go to StatTrak and find out what does the t-score of 2.4 mean with 4 degrees of freedom if you're using the approximate approach, 7 if you want to split hairs and do it the hard way. The results aren't all that different. If I do that, with 7 degrees of freedom, I get 0.97. 4 degrees of freedom, 0.96. Yeah, about the same. Meaning that there's a 97% chance that A is the better Hungry Hungry Hippo player. If they play an infinite number of games, A will win the series, eventually. 97% chance. That's the difference between individuals and populations. Again, there's a pretty big spread on B. Any given game, B could get lucky and win. There's about a 33% chance. With just a limited amount of data, I can be pretty darn certain, though, that A is the better team. A is going to win the match if there's an infinite number of games. And I guess that's what this says. Single game versus infinite series. I know more about populations than individuals. If there's a whole bunch of games being played, I have more certainty about who's going to win a whole bunch of games versus a single game. One other kind of sidelight, with a t-test, I can calculate how large the sample has to be. So for example, from this data, suppose I want to be 99.5% certain who the better team is. how large of a sample size do I need? Well, from the t-score, assuming 7 degrees of freedom, again, that's not quite certain, it's going to depend upon sample size. 99.5% certain corresponds to a t-score 3.499. So the mean versus 0, that's got to be 3.499 standard deviations away. So x over w is 3.499, or cross multiplying. 3.499 is, factoring at the end, assuming same sample size for A and B, I can pull that out. This I know, that I know, assuming it doesn't change with sample size. That's 1.05. So n has to be 11. Maybe rounding up to 12. 0.02 is pretty close to 11, but just be safe, rounding up. If I have a sample size of 12, I can be 99.5% certain about who the better team is. And also notice that since I've got this divide by square root of n, or I'm going to simplify, assuming same sample size for A and B, pulls it out, multiply by square root of n. As sample size goes to infinity, the t-score goes to infinity, making me more and more certain. In theory, with a large enough sample size, I can be certain about who the better team is, even for very, very minute differences. This is where the word significant is different for statisticians versus the general public. If I have two teams, one scores an average of 11.99 points a game, another team scores an average of 12.01 points per game, is the difference significant? Well, practically no, that's not a whole lot of difference. Statistically, that could be significant if I have a big enough sample size. So when you say statistically significant, that just means, given the data, can I tell the difference? Colloquially, difference just means, does it matter? So the two are different. Last example. Suppose I had 3 teams playing Hungry Hungry Hippo. Who's the better team? Well, the t-score doesn't really work in this case. The t-score really applies to just a single population, like A. I can kind of fudge it and say, if I have 2 teams playing, I could call this W is A minus B. Now, in terms of the numbers, this looks like a single population, W. When I have 3, I don't really know how to compare A, B, and C. If I had the actual raw data, what I could do is have, in the first match, A versus the maximum of B and C, A versus the maximum of B and C. Then I've got 2 populations. I can do W is A minus B and do a t-score. Oftentimes, you don't have that luxury. I don't have the raw data, or the sample size is not the same for all 3. In that case, if I just have the mean of A, the variance of A, and the sample size of A, likewise for B and C, there's not really a way to compare these with a t-score. I could say A versus B and A versus C, but really what that's doing is a single elimination tournament. If A had to play B and A had to play C, what's the probability that A will win both games? That's different than I just have 3 people playing. The highest score wins between the 3. So again, what we have doesn't really work. There is a way to do it. That's called analysis of variance, or ANOVA. That's one of the topics that we cover in random processes, but it's not really a t-score. That's actually an F distribution. But we'll leave that for when you take 341 random processes. So in conclusion, we've got the t-score. T-score works really well for a single population. I can sort of abuse the data. I can use it to compare 2 populations by changing the problem into a single population, A minus B. With that, I've got 2 ways to answer it. If I just want to know, for a single game, what's the probability that A is going to be bigger than B for a single game or a single sample? I form the variance is just the variance of A plus variance of B. If I'm dealing with populations, then it's the variance of A divided by sample size of A plus variance of B divided by sample size of B. And then I get, well, for populations I know more than I know about individuals. I'll get higher numbers about populations. And that's lecture number 15, take 2, correction, 16, take 2, for ECE 376.